So now let's look at our second queue example, which really does use the concept of queuing. So you can imagine this as maybe I'm doing my office hours, but this is pre-pandemic time. So if you want to come to my office hours, you have to come up to my office and knock on the door. So students are arriving at my office at some rate, let's call it lambda, and they have a problem that they want me to deal with, and that has some expected amount of time to deal with their problem. Let's call that 1 over mu. But the difference is here, when a student arrives, if I'm sitting in my office doing nothing, they can walk right in and I can start to try and help them with their problem. But if they arrive at my office and I'm already talking to a different student, they're going to have to queue up outside the door and wait. So if we call me the server who is giving this service of answering people's problems, here we only have one server, so only one individual can be served at a time. And so once I've finished answering someone's problem, if there's at least one person waiting in the queue, I'll then invite into my office the person who's been waiting the longest, and I'll start to answer their problem. On the other hand, if there's nobody waiting in the queue, then I'm free again. So again, we might want to analyze this as a Markov jump process, because we might want to know, is the queue outside my office going to get bigger and bigger and bigger, or am I eventually going to deal with everyone's problems and the queue will disappear? We might want to know what proportion of the time am I busy solving people's problem? What proportion of the time is there someone outside my door waiting? What's the average length of the queue? Those sorts of things. So again, we're going to start by writing down what the arrival and departure rates are for this queue, and then we're going to analyze it using techniques we've learned in the course. So this time we still have arrivals coming like a Poisson process of rate lambda. And the service times are still exponentially distributed with rate mu, but you only get serviced once you get to the front of the queue. So the transitions here are, again, we go up from I to I plus 1 at rate lambda. You go down from I to I minus 1. Well, if there's somebody being serviced, then the total number of people, that is, the person receiving the service and the people waiting in the queue, if there are any, that will go down by 1 when the person being serviced stops being serviced. Right, so that's just mu, because we're all waiting for the person receiving the service, the person who's in my office having their problem solved, for them to finish. And then everything will go down by 1. They'll leave. Someone will come into my office. The queue will go down by 1. So qi I minus 1 is mu for I bigger than 1, bigger than or equal to 1. Whereas, of course, q from 0 to minus 1 is 0. If there's 0 people, nobody can leave. And so, as before, because rows of this matrix have to add to 0, we have qii equals minus qi equals minus lambda plus mu I bigger than 1, or q0, 0 equals minus q0 equals just minus lambda, because there's no people leaving, there's only arrivals from 0. So if we draw a picture of this thing, it's basically like before, 0, 1, 2, 3, etc. Arrivals come at rate lambda, but now departures just come with rate mu. So it might be useful here to think about what's going on with the jump chain, the discrete time jump chain, which tells us where this process jumps. So each time it's going up 1, with probability, WP with probability, lambda over lambda plus mu. And it's going down, -1, with probability mu over lambda plus mu. We could call that P and we could call that Q. And we could see we have got back, for the final time in this module, our old friend, the random walk. It's not quite the random walk because when the jump chain goes to 0, the next thing must be a rival. So it's a random walk with a reflective barrier at 0. So the jump chain, which tells us just where we jump, is our old friend the random walk with a reflective barrier. So this tells us some quite important things to start off with. Right. It tells us that if lambda is bigger than mu, that means P, this P here, is bigger than 1/2, and that means that the chain is transient. That's a fact you might remember about the random walk with the reflective barrier at 0, is that if you're gradually drifting off to the right, you're transient. In other words, this Q gets bigger and bigger and bigger. In fact, tends to infinity. Now, that's very bad news, right? If people are arriving at my office hours quicker than I can answer their questions, then the queue, I mean, I might be able to deal with a few people's problems, but eventually the queue will just get bigger and bigger and bigger and bigger and bigger. And that is very bad news. So you don't want to be running one of these queues if the arrival rate is quicker than the departure rate, because otherwise the queue is just going to get bigger and bigger and bigger and bigger and bigger. If lambda equals mu, I mean, I guess lambda is never going to equal exactly mu, right? Lambda will presumably always be a tiny fraction bigger or a tiny fraction smaller. But if we just pretend it could be, then that would be P equals 1/2, and that would be null recurrent, from what we remember about the random walk with a reflective barrier. That's still bad news, right? The amount of time for the queue to clear is infinite on average. So the queue will eventually clear, but there's a good chance that it will take an extraordinarily long amount of time for the queue to clear. And so nobody wants to turn up to my office hours if the expected amount of time you have to wait for me to solve your problem is infinite, because you'll miss some lectures if you're waiting an expectedly infinite amount of time. On the other hand, if lambda is less than mu, which is P less than 1/2, then that means people are arriving slower than I'm solving the problem. So this is good news, right? This is positive recurrent. Which means the queue is going to clear in finite time. So this seems like good news. Right, the only good case is if people turn up slower than I answer their questions. That doesn't mean there'll never be a queue, right? Because just 2 people could turn up a bit quicker than you expected, and a problem could take a bit longer than I expected to solve. So I'm not saying there'll never be a queue, but I am saying that it will clear in almost surely finite time and expectedly finite time. So this is all good news. So for the remainder of this section, we'll only consider this lambda less than mu case, because the other cases are just bad news all the time. I should have perhaps mentioned a moment ago that we call this the MM infinity queue. The first M, as before, being memoryless arrivals, meaning that arrivals are like a Poisson process. The second M being memoryless services, and we don't call this MM infinity at all, that's a typo. We call this the MM1 because there's one server. There's only me asking the questions, and if there's more than one person, more than one individual in the process, they have to queue up and wait. So that's what the 1 stands for in MM1. Okay, so again, it would be interesting to know for this MM1 process, in the good case where lambda is less than mu, what happens in the long run. For example, what's the average number of people being serviced? What's the average amount of time people have to wait in the queue? And what proportion of the time am I busy asking people answering questions, and what proportion of the time am I free because there's no questions to ask? Those seem like interesting things to know. So again, to learn about the long-term behaviour, we're going to want to find a stationary distribution. So just as before, we seek a stationary distribution, and as before, that solves sum over I pi I qij equals 0, or pi q equals 0 in matrix vector form. So probability of coming down from I plus 1 is if there is departure, which happens with mu. The negative term on the diagonal is lambda plus mu. We saw that up there. And the probability of coming up from I minus 1 is lambda for arrival. We need it to be 0. That's the I greater than or equal to 1 case. I greater than or equal to 1, because we said that I equals 0 was different, right? That does have departures into it, and it does, but it doesn't have arrivals into it. That's just that for the I equals 0 case. And of course, because we're after a stationary distribution, we have the normalizing condition that this all has to add up to 1. So we could call this one the initial condition, and this one the normalizing condition, if you like, just so we know which is which. But note that what we've written down here is our old friend, the linear difference equation. Note that before we had some i's hanging around in the coefficients, which means that it wasn't linear. But this one just has mu's and lambdas hanging around in the coefficient. So that's just a good old-fashioned, it's a homogeneous linear difference equation because it equals 0 on the left. So it's been a while since we've answered a homogeneous linear difference equation. Hopefully we can remember what to do here, right? We start by writing down the characteristic equation and everything. So the characteristic equation is, well, we've got a problem here because the letter we used in the characteristic equation was lambda, wasn't it? It was something lambda squared plus something lambda plus something equals 0. But we're already using lambda for the arrival rate. So let's use a different letter. Let's use alpha for the thing in the characteristic equation, right? So this green boxed equation becomes mu alpha squared minus lambda plus mu alpha plus lambda equals 0. That's the characteristic equation. This one factorizes, doesn't it? We get an alpha minus 1, and we get a mu alpha minus lambda. Yeah, that all works out good as a factorization of the characteristic equation. So that means alpha equals 1 or lambda over mu. And remember, we're in the lambda strictly less than mu case. So lambda over mu isn't 1. Lambda over mu, in fact, is what last time we called rho. So we have distinct roots here, so no funny business going on. So the general solution is pi I equals a lots of 1 to the I, which is just a, plus b lots of rho to the I. Okay, but we've got this initial condition and this normalizing condition we can use to find a and b. So that should be all good. The initial condition is mu pi 1, which is mu a plus mu b rho minus lambda pi 0 minus lambda a plus lambda b equals 0. So that's a mu minus lambda a. Mu times rho. Rho is lambda over mu, so mu times rho equals lambda. So that's a plus lambda b, and that's a minus lambda b, and that all disappears. That cancels, right? So we're left with mu minus lambda a is 0. And again, mu and lambda aren't equal. So that means a must equal 0, giving us the solution pi I equals b rho to the I. Then finally, we can use our normalizing condition. We need a distribution, so this thing has to add up to 1. We need 1 equals the sum over I of b rho to the I. We can bring the b outside, and then that's a geometric progression, isn't it, rho to the I, because rho is less than 1, so that thing converges to 1 over 1 minus rho by the formula for a geometric progression. So b equals 1 minus rho. And finally, our solution is pi I equals 1 minus rho to the I. And that's the stationary distribution. Note, in fact, that that's a geometric distribution, isn't it? It's a geometric row. It's the version of the geometric that starts from 0. I don't know which type of geometric you learn. Some people start it from 0, some people start it from 1. This is the one that starts from 0. So now that we have a stationary distribution, we can answer everything we want about the long-term behaviour, right? The average number of people in the process is the expected value of geometric row, the geometric that starts from 0, which, if you remember, that's rho over 1 minus rho. Putting in rho equals lambda over mu. Lambda over mu, 1 over lambda minus mu, which is lambda over mu minus lambda. So that's the expected number of people. That might include 1 person in my office hours, and then it might also include some people waiting in the queue. Note that if lambda's just a little bit bigger than mu, a little bit smaller than mu, then that denominator gets very small and that number gets very big. So if I'm only just dealing with people quicker than they're arriving, then the queue can be quite long on average, but it will clear in expected finite time. So you might have to wait a bit, but it's not super serious like the null recurrent case, and it's not terrible like the transient case. Similarly, what proportion of the time am I busy or idle, not answering any more questions? Well, by the ergodic theorem, the amount of time I'm idle is pi 0 when there's nobody in the process. And for a geometric P, that's 1 minus rho, isn't it? Which is 1 minus lambda mu. So I'm busy a proportion 1 minus pi 0 equals rho equals lambda mu of the time. So again, if lambda's only a bit smaller than mu, then lambda over mu is close to 1, and I'm busy most of the time. And so that's all I really wanted to say about those 2 models for queuing processes and their applications of what we've learned in this course. And that brings us to the end of the mathematics for this course. In the next section, we'll have a bit of a summary and say a few words about the exam.